Welcome to this explainer. Okay, let's just dive right into it. Today, our goal is to completely demystify the fundamental anatomy of modern robots. If you've ever looked at a massive robotic arm on an assembly line or a rover cruising around on Mars and wondered how it all actually works together, you are definitely in the right place. When we picture advanced robotics, it can honestly seem like pure science fiction or even magic. But the truth is, every single system out there, no matter how incredibly complex it might appear, ultimately boils down to just four primary, highly interconnected components working in perfect harmony. So here's our blueprint for today. 1. The anatomy of a robot. 2. Sensors, perceiving the environment. 3. Controllers, the robot brain. 4. Actuators and gears, motion. And finally, number 5, the integrated robotic system. So, here's the crucial question we really need to answer as we go through this. How exactly does a literal pile of inanimate metal become a functioning, adaptable robot? Like, how do these completely isolated parts actually interact with and dynamically adapt to a totally unpredictable, real-world environment? All right, let's start with section 1, the anatomy of a robot. To build the skeleton of our machine, we've got to start with the absolute most basic building blocks of physical movement, and that's gears. Think of gears as, well, the human joints and leverage points of our mechanical skeleton. Their main job is the transmission and amplification of force within the system. They are absolutely key to controlling rotation and making sure the robot has the actual physical strength it needs to operate. To ground this abstract concept in reality, let's look at some tangible applications from our source material. Gear trains are used specifically in robotic joints to meticulously control rotation and torque. Then you've got planetary gears, which are used for really specific heavy-duty force transmission. And worm gears, these are incredibly effective at helping amplify force in those super intricate robotic joints. Moving right along to section 2, sensors, perceiving the environment. Now that we've got our mechanical structure set up, it desperately needs to see and feel its surroundings, right? It needs sensory organs. So sensors are devices that detect and measure physical quantities, and they provide real-time feedback and data straight to the control system. They're actively perceiving objects, obstacles, and shifting environmental conditions. This real-time data feed is completely vital because it's what actually informs the control system, letting the robot constantly adapt to changes. To pull off the kind of precision needed for complex interactions, robots rely on a whole variety of sensors. You have vision sensors, so the robot can effectively see what's around it, proximity sensors to detect nearby objects, to avoid crashing into things, inertial sensors constantly monitor movement and balance, which is actually very much like our human inner ear, and finally, force or torque sensors act kind of like a sense of touch, detecting the exact physical forces that are being applied to the robot. Next up is section 3, controllers, the robot brain. So moving up the chain of command, with all this sensory data constantly flooding in, the robot obviously needs a powerful brain to handle it all. Controllers are the computational units that process that sensor information, make the decisions, and then send precise commands out to the actuators. Think of the controller as the master orchestrator. By relying on pre-programmed logic or blazing fast real-time computations, the controller is coordinating multiple, completely different parts simultaneously to achieve precise, coordinated movements. To give you an idea of what these brains actually look like in the real world, we can start with basic microcontrollers or microprocessors. Those handle your simpler tasks. Step it up a notch, and you've got programmable logic controllers, or PLCs. These are heavily relied upon in massive industrial automation factories. And then, right at the top end, there are highly specialized robot controllers designed from the ground up for incredibly complex robotic systems. All right, let's get moving with section 4, actuators and gears, motion. Okay, so we know the controller has made its decision, but now the robot actually needs its muscles to physically act on it. This creates a really clear distinction in our system. On one side, sensors act as the inputs, gathering real-time data from the environment. On the other side, actuators act as the outputs, pushing physical movement directly back into that environment. The crucial point is right here in the definition. Actuators are devices responsible for converting energy into motion, generating the physical movements required to perform tasks. I really want you to notice that action verb, generate. These actuators are what actually control the robotic limbs, the joints, and the end effectors, which is what allows the machine to physically manipulate objects and actively navigate its space. And there is just a massive variety of these robotic muscles. We have electric motors driving precise joint movements. We use pneumatic actuators when a very specialized force is required. Linear actuators are utilized specifically for producing straight-line motion. And then, of course, we have grippers, acting as those end effectors we just mentioned, which are totally essential for actually picking up and physically manipulating objects in the environment. Which brings us to our final part, Section 5, the integrated robotic system. This is where the magic really happens, bringing all these isolated anatomical parts into a closed-loop system. Let's walk through it step by step to really cement how this works. Step 1. Sensors provide vital environmental feedback in real time. Step 2. Controllers instantly interpret that data and make dynamic, on-the-fly decisions. And Step 3. Actuators and gears execute those coordinated physical movements based on the controller's exact commands. It is a continuous closed-loop cycle of feedback and action, letting the controller constantly adjust the actuators based entirely on what the sensors are experiencing out in the real world. Our final thought from the source material today really brings it all home. The integration of these components is essential for achieving precise, adaptable, and efficient robotic operations. It's honestly fascinating how this continuous, perfectly orchestrated teamwork breathes life into modern automation. So I'll leave you with this. The next time you see a robot seamlessly completing a task, ask yourself, what invisible symphony of sensors, computing, and actuators firing is playing out in that exact millisecond?